All right, this is the notes for lesson 7-2. So this is exponential growth and decay, and they're all word problems. So I can solve exponential growth problems and exponential decay problems as our learning target. So we start out with, our regular exponential a and b to the x, and we're going to assign them kind of different things in this video. So a, you're used to it being the y-intercept. A is the initial amount of whatever you're starting with. So you start with something and it either grows or decays, but whatever your starting amount is, that's what we're going to put where A is. B is the growth factor. So for growth, it's going to be greater than 1. For decay, it's going to be less than 1. And it's written like this. We'll talk about this when we get to the problems. R is the rate or decay rate. So R is normally, in the problem, will be a percent. But write yourself a note here, as we never do math on percents. So these values we're always going to change to a decimal. Okay, before we do math on them, we're going to turn them into a decimal. Just a reminder, the way you do that is you divide by 100. So percent, think per century, means per 100. So whatever the percent is, you're going to divide it by 100 to get your decimal. X is like your input, which is often time, because we're looking at how things grow or decay over time. If B is greater than 1, we have growth. If B is between 0 and 1, we have decay. So remember, 0 and 1, that could be a decimal or a fraction. Think of your measuring cup. A decimal or a fraction that's less than a cup, but more than 0. These are what your formulas are going to look like. So if you think about it, this 1 plus R here is your B. So our base comes from taking 1 plus the percentage rate that they give us. So when we have a plus in here, we're going to have growth. So this is something getting bigger over time. As X increases, Y increases. And remember, this X, you can think of it as time. As a matter of fact, a lot of books will write these formulas, and the variable they'll put here will be T for time. So the plus gives us growth, the minus gives us decay, and once again, your X is going to be time. This is what happens when something doubles, right? So I think we had that problem about, would you rather have $1 million or a penny a day that doubles? The 2 to the power of X means whatever you're starting with is going to double for each time period. And then this is the same thing. So this is definitely growth. And then this is decay, because our B is between 0 and 1. And this is half-life. So this is the one that you learned about probably in science. So what we're going to do is look at an example of each type of these problems. Now the one thing I don't like about these notes is that they tell you what kind of problem it is, but I want you to think, well, what if I didn't have this right here? How would I decide which one of these formulas am I going to use? So we're going to look for some keywords. So the first thing we do is read always. An experiment begins with 300. So begins with 300. So this is your initial amount. And if you look up above, that is our A. And the population doubles. Here's the keyword that tells me I'm going to be using this formula for doubling. Every 30 minutes. This is how often it doubles, right? This is a time. So I'm just putting some labels underneath what I have here. The doubles, I can tell myself, this is the doubling formula. And how many bacteria will there be after 2 hours? Okay, so we know we're using the doubling formula. Whoopsie. Which is A 2 to the x. Okay, now I have to figure out what we're given and what we're solving for. Well, We already said that this 300 was what we're starting with, because that's our initial amount. So I'm going to plug in 300 for A. And then this 2 is part of our formula. So Y is what they're asking us to find, the final amount. Okay, now the time is 30 minutes. But what you have to think about here is they're asking what happens in 2 hours. So I don't want to put my 30 minutes up here. I want to figure out how many 30 minutes in 2 hours. Well, there's 2 30 minutes in 1 hour, so there's 4 30 minutes in 2 hours. So my T, or my X, is going to be 4. So that is what is going in here. So this kind of tells or explains how I got that 4. So then I would put all this in my calculator, and I would get 4,800. Story problem requires a story answer, so always include units. And in this case it would be bacteria. Now I'm going to show you something, because this is just a short time period for, I'm going to show you how you could actually do this without this formula, but you could use it to check. So think, if I start with 300 and it doubles every 30 minutes, after 30 minutes I would have 600, right? It would double. And after 30 more minutes, if I double 600, I get 1200. And then after 30 more minutes, I would have 2400. And then, oh, I'm running out of room here. After 30 more minutes, if I double 2400, I would have 4800. So that's 1 hour, 2 hours. So that's what I would have in 2 hours, the 4800. And that's exactly what we got. So that's kind of how you could check this to make sure you plugged everything into your formula properly. If you had put 30 here, you wouldn't have gotten this 4800. Then you'd know you did something wrong. So let's think about this one. This is the same problem, but they're asking in 10.5 hours. So I want to take my 10.5 hours, and if you think about it, I'm dividing it into 30-minute increments or half-hour increments, right? So that is going to get me 21, which is going to be my T or my X. So in 10 hours, there's 21 30 minutes. So what I'm going to plug in my formula is same initial amount, but this time 2 to the 21st. Okay, if you think about this, if I take 30 minutes times, 30 minutes, 21. So plug this in your calculator, and what you get is a really big number. 629,145,600 bacteria. So this is not one you would want to check this way up here, because I'd have to do it 21 times. But you can see it's growing really fast. So 2 hours, 4,800, 10 hours, 629 million. That's exponential growth. It gets big very quickly. Okay, spend some time, make sure you understand this conversion, and pay attention to that whenever you're given 2 different units. You need to convert, in this case, your minutes to your hours. So that's doubling. All right, turn the page. This is decay. So remember, in decay, whatever your initial amount is, your final amount is going to be less. So decay means something is decreasing. And if we remember our decay graphs, they looked like this, right? So as X got bigger, Y got smaller. So this is, you buy a new car for $3,500 in 2008. It depreciates. Depreciates means it's losing value. That's the term they give to how much value an item loses over time. So, you know, a new car is worth this. In 10 years it's worth less because of depreciation. This is the depreciation rate. So this is our R, but we need to convert to a decimal. So remember, we don't do math on percents. We got to convert them to a decimal. So if we bought it for $3,500, this is going to be our A, our initial amount. So what's happening here? We have decay. So our formula is going to always start with our initial amount, but because something's getting smaller, we have a subtraction in there. And then remember, our X is our time. So let's think. We decided we bought it for $35,000. So that's our initial amount. 1 and minus is just a copy job. R is 18%, but we're going to put in 18 divided by 100, which is 0.18. So 0.18. So percent to decimal, you move the decimal 2 places to the left. But if that's confusing, remember you're just dividing by 100. Okay, and what is our time? Write an equation for the car's value X years after 2008. So this one, we're just writing an equation. They didn't give us a time. So this is an equation that you would use to calculate the amount now given a certain number of years. So it just asks for an equation, so I'm done here. All right, what about this one? Now they say, what will the car's value be in 5 years? So now we know time, or X, is 5. So I want to go back to this equation, and I want to find what happens in 5 years. So everything's going to be the same, but X is 5. Now remember, this is depreciation, so the answer I get here, the final amount, should be less than my initial amount. So put all this in your calculator, and I'm going to remind you, if you put it in your calculator just like this with parentheses, you'll be okay. You can put the whole thing in your calculator, but make sure you're wrapping up this in parentheses. And what we get is 12,975. This is money, so we want to go to the cent, so 2 decimal places. Story problem requires a story answer, so that always means units and or words. In this case, just units, which would be dollars. So the car is now worth $12,975.89. Okay? I don't know what the depreciation rate is. I don't really know if that's a reasonable rate or not. All right, let's do another, and then maybe... well, I'll see if I've split it into 2 videos or not. Okay, this is growth. So this is kind of like the doubling, getting bigger. Okay? So a computer engineer is hired for a salary of this. So this is sounding like the initial amount, but let's keep reading. If she gets a 5% raise each year, this is definitely our R. The nice thing about R is it stands for rate, and that's a percentage rate. If she gets a 5% raise each year, after how many years will she be making $100,000 or more? So it's growth. Even if it didn't tell me that, I know it because the initial amount and the final amount are increasing. So even if I didn't have this growth here, I would say, oh, well, something's getting bigger, so that's growth. The other thing you want to pay attention to here is, what are they asking for? They're asking for years. So my X is what I'm finding. So a little different than these other problems where we were always solving for Y. So it's asking for time. Okay, let's write the equation for exponential growth. Y equals always the initial amount. And when something's growing, we put a plus in the middle, which makes sense. Remember, these are exponentials, so your variable is stuck up here as an exponential. Now she got hired for $70,400, so this is our initial amount. And then what this 100,000 is our final amount. So in all these equations, the A is the initial, the Y is the final. We know the R, we're going to be solving for the X. So let's plug in 100,000 for final. Initial is 70,400. 1 plus 0.05. Turn it into a decimal, and X is our unknown. So we're solving an exponential because our variable's up here. So this is like a Unit 6, Unit 7 problem. So first thing we always want to do is isolate our variable on one side of the equal sign. So I'm going to undo this multiply by 70,400 by dividing both sides of the equation by 70,400. So those two won out. I'm going to move over here. And on the left side of my equal sign over here, I'm going to have 1.4204. Don't round too much. Do a good 4 decimal places here, okay? And then on this side, I'm going to have 1 plus 0.05 to the X. Alright, this, I can combine those like terms inside those parentheses. 1 plus 0.05 is going to be 1.05 to the X. Okay, so this is solving an exponential. Now the first way we learned in Unit 6 was to get a common base. Well, we're not going to find a common base with these decimals. So we want to convert this or rewrite it as a log. Normally when we did this rewrite, our exponential was on the left. So I'm just going to flop this around and put our exponential on the left. Okay, now I'm going to do my rewrite. So exponential base 1.05 is going to become log base 1.05, remember the bases always match, of 1.4204. First arrow is everything on the left side of the equal sign, equals X. Okay, this is just a number. I can put this in my calculator. If you have an TI-84, you can put this in right now. Remember, use the math button and go all the way down the menu till you get to log base. If we don't have a TI-84, then we're going to do that change of base. So we're going to rewrite this as log of 1.4204. So this is what you learned in 7.1 over log of 1.05. And that's going to equal X. So that's what you're going to put in your calculator. And then you should get 7.1870. Now I think you should be punching this in on your own and verifying that you're getting these same numbers. Okay, now the next thing you want to always check is your answer reasonable? So remember, we're finding time here, we're finding years. So this would be 7.187 years. So let's go back and think, is that reasonable? She started at 70,000, she's going to 100,000, she's getting 5% a year. So how can I see if that's reasonable? Well, one thing I can do is grab my calculator. I got my ancient calculator here. And let's do 70,400 times 1.05. That would be her raise for 1 year. So that's at 73. Let's do it again. Times 1.05, that'd be 2 years. Times 1.05, that'd be 3 years. So we're at 81,000 now. So I think if I kept doing that, I'd be close to 100,000 in 7 years. So that does seem reasonable. So make sure your answer is reasonable. If you got an answer here of 4,000, you should say to yourself, that doesn't make sense. I must have a mistake somewhere. Okay, so make sure it's reasonable. I'm going to go ahead and do this next one. And then maybe we'll do one of these in class together. Okay, so this is half-life. Well, half-life problems usually have the word half-life in them, so that's going to be your clue that you're using half-life. And this has years. Okay, so now the one thing you need to be careful about in half-life is half-life formula. I'm going back here. This X is normally half-life periods. And they'll often tell you how many half-life periods there are, or how many years there are in a half-life period. Let's see if this problem has that situation going on. So this is our element that we're dealing with. They tell us it has a half-life of 1,620 years. That means whatever you start with, it's going to decay to half its amount, and it's going to take this many years to do it. So say if you started with, I don't know, 100 grams, after 1,620 years you'd have half of what you started with, so you'd have 50 grams. So that's what half-life means. I'm going to go ahead and write the half-life formula here because I know that's what I'm using. Same thing, initial amount, base is a decimal between 0 and 1 because it's decay. So it says write an equation for the amount of radium-226 remaining if there is currently, there we go, there's our A, our initial amount, 550 grams after X half-life periods. So we're just writing the equation in this one. So the equation would be the final amount is going to equal our initial amount, which is 550 grams, times 1/2 to the power of X. Alright, so that's our equation. This just asks for an equation. Okay, this one says how much radium-226 will remain, here's what I'm talking about, after 3 half-life periods. So I want you to go back here and make sure you put this in your notes, that this X is not time, it's half-life periods. So either they give it to us, sometimes we have to figure it out, how many half-life periods there are. This time they gave it to us. So I can say that my X is 3. So the time in this formula has to be half-life periods. So I'm using the equation I wrote right here, but in place of X, I'm putting 3. Now remember, I should have less than this. It's decaying. So if I put all this in my calculator, just like I have it written, I will get y equals 68.75. And I need some units. Always, always, always. Where are they? Here they are, grams. So this would be 68.75 grams. Make sure you include units. So yep, it's decaying. That sounds reasonable. Remember, 3 half-life periods is 1,620 times 3. It takes a long, long time. Alright, now this says how many years are equal to 3 half-life periods. So this is kind of getting you ready for those problems where you have to figure out how many half-life periods you need when they tell you years. So let's just think. In 1 half-life period, there is 1,620 years, because that's what they said up here, has a half-life of 1,620 years. So in 2 half-life periods, there's going to be 1,620 times 2. And in 3, I'm going to do this little quote, which just means copy these words from above. I'm going to have 1,620 times 3, which gives me 4,860 years. So in this 3 half-life periods that we plugged in up here, 4,860 years have passed. Okay, that is it for 7-2. Well, you guys will have some practice, and we might look at 1 or 2 of these in class. Okay, that's it.